Hi, I'm John Forrow from Autel. Welcome to the second part of our three-part series on making hybrid and electric vehicle repairs easy. Those of you that attended last month's webinar know that we covered battery management systems and stuff to do along with those particular systems. In tonight's webinar, we'll do a quick little refresher. Not going to spend a whole lot of time and go as in depth as we did last month on some of the parts of the BMS, but we're going to concentrate more so on the inverters and converters and also the motor generators and how they work. Remember, if we understand how they work, it's going to make it very easy for us to apply that knowledge to help us diagnose and repair the vehicles. At the end of today's webinar, I'm going to share with you my go-to PIDs when it comes to electric drive vehicles. These are the PIDs that I look at all the time, no matter what type of vehicle comes in, as long as it's hybrid or plug-in hybrid or full electric. Those are my go-to PIDs to help me locate what the customer's concern happens to be. So just as a quick refresher, going over the slides, you guys have copies of these slides in the GoToWebinar. I placed them in there for you. We're only going to use the first couple slides, the rest of it's going to be hands-on. The most important part that I found that makes it so much easier for technicians to understand is if we can associate what the goals were of the engineers when they built an electric car and how they achieved those goals, it makes it so much easier for us to understand how these systems work. So the main goals were they wanted it to be like a car. They needed to start and stop. They needed to have good battery range throughout, as long as period as possible. They want to make sure that it does car stuff. They still need headlights and 12-volt, circuitry, but they also needed to go ahead and go forward, go backwards, all that kind of stuff. So the final goal that they had was they wanted it to make sure, we're dealing with high voltage, they want to make sure that it's safe, right? So that it's safe for not only the driver of that vehicle, but also fairly safe for the technicians as well. So if you remember, as far as the safety part goes from last month's webinar, all of that high voltage is kept inside the high voltage battery pack until we close those high voltage switching contactors. And remember, those are closed with 12-volt current. So all the rudimentary systems such as the brake on off switch and the park reverse neutral switch and all that stuff still applies. Once all those conditions are met and you hit the start button on the dash, that's when there's a signal sent along the CAN data bus to go ahead and close the high voltage switching contactors. And from last month's webinar, again, there's a picture of the actual high voltage switching contactors. We talked about using the scan tool to diagnose those in last month's webinar, so I'm not going to spend a whole lot of time referring back to them in tonight's webinar. And we even went ahead and showed a little box that I made up that I use in live training classes across the country of a safe way for us to fully understand how the high voltage switching contactors work. So again, we're not going to go over all that in great detail tonight. We spent an hour and a half last month going over battery management systems and that being part of the battery management system. So we're going to start with inverters and converters. The reason why we're going to start with that is from experience, that's the hardest thing for relatively new technicians into the electric vehicle realm of diagnostics, has the hardest time grasping how they work. If you think about it, it makes sense. We had a 12-volt battery before, so taking that prior foundational knowledge and applying it towards a high voltage battery isn't that big of a leap in faith here. We also had tons of motors on vehicles before, so we had alternators and stuff. So the motor generator isn't a totally new concept either. We already have a good foundation for that. But inverters and converters, we have nothing as far as foundation goes. So I wanted to start with that. And I'm going to go ahead and I have a sample inverter converter assembly here. I'm going to take it all apart. I'm going to show you the components inside, and as I do it, I'm going to share with you what the purpose of those components happen to be. But as I'm going through it, think about it analytically, because if you understand, if I hold something up and I tell you what its purpose in life is and how it works, think about the data stream, right? And how you can interpret the data stream to help you diagnose a problem that may be affected by that faulty component. So that's the key thing that I want to stress that we try to think about, is put on our analytical thinking caps and actually concentrate on that. We're going to summarize this whole webinar up at the very end, and we're going to go ahead and show you those go-to PIDs, and we'll use a little refresher explanation of stuff that we went over. But if you can start thinking that as we take these components apart and do the testing and stuff, that would make life a lot easier, and it will help you better understand to be an ace diagnostician when it comes to electric drive types of vehicles. So I'm going to go ahead and get started with this inverter converter assembly. This is actually out of a Toyota hybrid, so it's nothing that's a full electric, but the components are the same, whether it's a hybrid, a plug-in hybrid, or an electric vehicle. There's only one extra component that we talked about last month on a full electric vehicle. It's called an onboard charger. It could also be found on some plug-in hybrids, but the components inside the onboard charger are very similar to an inverter. And even some electric drive vehicles will still have both an inverter plus an onboard charger. But realistically, a lot of manufacturers, since they use the same components, will do away with the inverter and now call it an onboard charger. So we're going to keep referencing those goals that the car manufacturer had as we go through this. And I'm just going to go ahead and start by taking the top cover off. And on a vehicle, basically the way this works is once the high voltage switching contactors that we talked about last time, once those close, it will send the high voltage from the high voltage battery pack out to the inverter assembly. Some vehicles will use a high power distribution module, so it'll send it there first and then it goes to the inverter assembly. But most of them will use something like this. Now remember, they wanted to make it safe, right? So the car manufacturers with the high voltage use an isolated ground. An isolated ground basically means the high voltage does not use chassis ground on the vehicle. There's a lot of safety features built into this, right? So one of the safety features built in is we will set codes if that isolated ground is compromised. We'll talk about how that can happen here a little bit later on. We also have something built into electric drive types of vehicles that in the case of an accident, those high voltage switching contactors located inside the battery pack will open back up. So as soon as the capacitor is discharged, we're not having live high voltage anywhere outside of the actual high voltage battery pack on the vehicle. So anytime a vehicle's in an accident and it's bad enough to deploy airbags, on the side of the unit over here is an extra crash sensor or impact sensor that actually is used so that it's triggering sharing the information along the data bus lines of communication, saying, hey, I was just involved in an accident. Later model vehicles will use something called a pyro fuse. Same exact principle, right? It's a way that it's going to disconnect the ability for those high voltage switching contactors to send the power out of the high voltage battery pack. Another safety device that has is something called an interlock. So the interlock is on the bottom side of this cover. When I put this back on, it will actually be pretty much a shorting bar. And that shorting bar just tells all the electronics in here that that cover is safely installed. Now, if I wanted to do live testing and I had to take the cover off and I wanted to do some voltage checks or scope checks or something in there, I would have to go ahead and remove this shorting bar and plug that back in. But the most important thing, remember we beat on this pretty hard last month, is we want to make sure that we have our personal protection devices on, so our high voltage gloves and stuff, if we're going to be measuring live circuits on high voltage. So with that being said, the rest of this is just a tin cover. Not that important for what we want to talk about here. So I'm just going to place that off to the side. When I look at the components inside the inverter, and Toyota is kind of unique, they bolt the converter to the bottom of the actual inverter. We may be a little bit intimidated by this. I took the time for in live classes, I've labeled all these components and stuff, but not a big deal. I'm going to explain them to you as I take it apart. So I'm going to take the first unit off here and we'll talk about what the component is, if there's any dangers involved with the component, what the component's used for, how the circuit actually is designed to work for the component. So we're going to give a lot of information, hopefully in a short amount of time here. And ultimately, our goal is it's going to give us a much better understanding of how these systems work. Now, I will say this, not all cars are like this, but as far as the Toyota inverter assembly goes, every component in here can be purchased and can be replaced by itself. So that's good. If you know what's wrong, you can buy one little component of this instead of buying the whole inverter. The converter side of things is a little bit different story. So I've got the first component out. Just put those bolts down. This is called the capacitor assembly. Now, this is what I like to refer to as the murder weapon on a high voltage car. So everything we've heard from our hybrid training classes of years past about using the orange gloves and doing a live dead live test and all that stuff, that was all because of this, right? When we send the current from the battery pack by closing those high voltage switching contactors, that current goes right to the capacitor assembly. Remember, that's why we had a pre-charge relay involved in that circuit from last month, because this is basically just going to be a short circuit, right? If I just send high voltage right to this without regulating it in any way, we run the risk of causing damage, right? So we would allow the negative voltage to go right to it, 100%, the negative cable. The positive cable had to go through the main resistor. Then using Ohm's law, we were basically controlling the inrush of current when this gets charged. Now, we now know how this gets charged, but what is it used for, right? So I've got all this current, and a capacitor is like a little storage battery, right? This is how this could damage us, because even if we disconnected the high voltage circuit, these may still have a charge in them. So if I started touching those dangerous orange wires without protective gloves on before these capacitors are discharged, that's where I run the risk of getting electrocuted. So what do they use it for once it's charged up? Well, this is what's actually being used to drive the drive motors on an electric drive vehicle, right? This along with some of the available battery voltage. How does it get discharged? Well, it gets discharged two ways. In normal operation, it gets discharged every time you step on the gas pedal and want the car to go, right? But it immediately charges back up. But once you power the system down, it needs to bleed off that stored energy. So on the side of it is the resistor block assembly. Now this is what Toyota uses. Some other car manufacturers use something similar to this. Other vehicles will just use a heavy-duty ceramic resistor, which they'll call a main resistor, to actually bleed that stored energy down, which is why some manufacturers will tell you, if you look at your information system, that once you go ahead and disconnect the high voltage circuit, to wait 5 minutes, wait 10 minutes, whatever it happens to be, and that waiting time is allowing that stored energy in the capacitors to dissipate. But never take the word for it that the car's working properly. It's in your shop for a reason. So if for some reason this resistor assembly was burned out, well then it's impossible. It doesn't matter if it told me to wait, 30 seconds or 30 hours. It's not going to be able to discharge that, which is why you always want to prove it with yourself before you ever take your high voltage safety gloves off. So now that we know what the first component here is, I'm just going to place that off to the side. We see the rest of the components available inside this inverter at this point. I'm going to start going ahead and removing the rest of these components. So I'm going to start with the most simple thing, but they are important. These are called bus bars. Now, no matter how much experience you have with high voltage, you'll get the general concept of that. There's going to be two main bus bars, and basically we have two because a Toyota Prius will have a motor generator 1 and a motor generator 2. Notice that there's 3 terminals on each one of those. So that is the 3-phase circuitry. So basically we are sending current through these bus bars, and then the other side of the bus bars will have a little cable that looks very similar to this, and this would actually bolt up inside the inverter. The other side's going to go down, in Toyota's case, to the transaxle and make the connection, the physical connection, to the stator windings of the motor generator. So the bus bars, they're responsible for transferring the current from the IGBT module, which we'll talk about here in a second, over to the harness that eventually goes down to the actual motor generators. So let me get these out of the way here. And I've got to switch my tooling setup because the rest of the bolts use Allen heads as opposed to 10 millimeters. Make sure I got the right Allen head. And it doesn't much matter in what order I take these apart. It's more important that we talk about what the components are. So I'm just going to start removing the components here and holding them up and talking about what they actually do in the world of electric vehicles. Okay, so it always helps to have a little magnet because these spots are pretty small to get your fingers in. So let me get these bolts out of the way. I'm going to remove the one little connector here that's going to be holding it in. And I went ahead and I removed the IGBT module. Now the IGBT module, insulated gate bipolar transistor, there's obviously a little computer inside here as well, right? But the IGBT, those insulated gate bipolar transistors, in conjunction with the actual MOSFET relays, is how we create the voltage and AC simulator voltage to be able to drive those drive motors, right? So let's talk about this for a little bit here. I said before that we had a pretty good understanding of motor generators. So we'll talk about motor generators here real quick. This is actually an alternator. Don't worry, I have a motor generator that we're going to graduate to here in a second. But here's the 3 phases, just like a real live motor generator will have on the stator windings. And we also have a rotor assembly, just like we did in an alternator. We know that this guy created AC voltage. We needed to go ahead and invert that AC voltage to DC voltage because the car's batteries are always DC, right? So with that being said, this is creating AC voltage. A motor generator can create AC voltage as well during times of regenerative braking, which we'll talk about a little bit later on. We have to drive a motor generator with AC voltage. Where are we getting it from? How are we obtaining this? How does that work? Because our high voltage battery pack is DC. So the job of the inverter is to invert AC to DC or DC to AC depending on what it needs. So in the old-fashioned alternator, we had some components. And we had something called a rectifier bridge and we had a diode trio. And these two components working together would actually go ahead and not allow this AC generating alternator to send AC voltage back to the DC 12-volt battery. Instead, we would convert that over to DC voltage, and then obviously there's voltage regulators and stuff to make sure we didn't overcook the battery. So with that being said, this is not a real new concept to us, but how does an actual electric car go ahead and invert the AC voltage to DC or DC voltage to AC, whichever way it needs? Well, this is part of the reason right here. So this here, those MOSFET relays, which we're going to talk in greater detail about and show you how to test them and stuff coming up, in conjunction with the IGBT, insulated gate bipolar transistors, are basically like rapidly closing switches. That is kind of like the actual diode trio of the old-fashioned alternators, right? Now we know that that's only half of what we need though to be able to do that conversion. So the other part, the workhorse, just like in an alternator, you knew this was the real workhorse because, hey, it's manly, it's got cooling fins and everything else. The other part that's the workhorse is the component that I'm going to talk about next. So I'm going to take this off. Got more bolts to remove here. And this next component that we talk about is going to be called the reactor inductor. Now, get all these bolts out of the way. This, pretty manly. Just like how in the alternator, the rectifier bridge, you knew that did something important. I know you guys can't feel the weight of this, but this is kind of heavy. This is the heaviest component inside this whole assembly here. With the MOSFET relays and the IGBT transistors, in conjunction with this, this is how we go ahead and transform AC to DC voltage or DC to AC voltage. So we got one other component in here, and not all vehicles will have this depending on the vintage of the electric drive vehicle it is. So this is just the 12-volt circuitry harness. All of this stuff inside here is controlled with 12-volt circuitry. So I'll just put that off to the side. We have something called a boost control. Now the boost control is used on later model vehicles because if you remember the history of hybrids, whenever I accelerated the car on early hybrids or whenever the air conditioner was turned on or anything along those lines, it forced the gasoline engine to go ahead and start up because we did not have, it takes a lot of current to take a stationary object and get it to start going down the road. So somewhere around late generation 2, generation 3 on Toyota's case, we came out with the boost control. A lot of vehicles use that today. And what that basically does is even though I might be dealing with, say, a 200 or a 400 volt battery or whatever the car happens to be, for a split second when you're stopped at a stoplight and the light turns green and you step on the gas pedal, I can boost that voltage up. So in Toyota's case, I could go as high as 580 volts. So basically how it's doing that is it's discharging the capacitors, plus we still got current inside the battery. So at that point, I can take that stationary object and get it to start going. Now, the last three components we talked about, the boost control, the actual reactor inductor, and the IGBT, the bottom side of them are a heat sink. And actually, we will have special grease, heat dissipating grease, that needs to be evenly applied when we replace one of these units. And this needs to be torqued down so that it can help dissipate the heat. Now, you'll see how it dissipates the heat as we take this further apart. At that point, the actual inverter assembly is 100% empty at that point, right? Nothing else inside there. Now, if I flip it upside down, we're going to start talking about the converter assembly. So I'm going to find my little tools here again, change the bits in it. First, I'm going to start by just taking off the actual cover. And usually in a live class, people say to me, how many times have you taken that inverter apart? And honestly, I don't have an answer for that. It's a lot. It's probably if not 1,000, close to 1,000 times that I've taken these things apart. Now remember, everything we just talked about, if you determine it's bad on a Toyota, for instance, you can pick up the phone and you can order those parts. Save the customer a bunch of money, just replace the faulty component. Now, a couple interesting things here. So this is just a tin cover to cover the DC to DC converter. Job of the DC to DC converter is to change the value of DC voltage, right? So I'm not converting AC to DC or DC to AC. That's the job of the inverter. The converter's job is to change a value. So why do I need to change a value? Well, we don't have an alternator on an electric drive vehicle. I still have a 12-volt battery, however, that needs to have a charging system. So I can take the high voltage system and I can go ahead and put out, say, a 14.8 volts so that I can keep that 12-volt battery charged, right? Notice that there's no interlock, no safety interlock on this cover. That's not always going to be the case. In Toyota's situation, they don't feel that they need one on here because the way how this is installed on the vehicle, you have to have this out of the car. You have to have all the high voltage wires disconnected and everything to be able to get to this cover. It's impossible to do while it's on the car. However, the top cover, right out there in the open, I could easily take that off and do some testing, right? This one here, they assume if you're taking this cover off, it's out of the car on a bench, right? Definitely all the wiring has been disconnected. So they don't need that safety interlock on the DC to DC. Now I'm gonna go ahead and remove the actual DC to DC converter from the inverter body. Now, nothing in the DC to DC converter is replaceable. So if you determine that this component is faulty, you need to order this whole assembly in Toyota's instance. So here's the componentry inside here. This side is the part that's responsible for going ahead and they call that a buck converter to lower the voltage down, right? So this is what's in control of charging the 12-volt battery on the vehicle. But you'll notice there's other stuff in here. Here's an AC fuse, right? Newer model Toyotas, they make that much more user-friendly to actually change at. I've got my actual harness coming out of the side of this, which is going to end up going over to the AC compressor side of things. Here is how these wires, how we power this DC to DC converter up. I got two wires going through the inverter, and they actually attach on the positive and negative stud inside the inverter. So, with that being said, on the back side, this is a little silver bullet for you guys. Toyota does not use a gasket, they just use RTV. It's common for that RTV to start leaking. There's a cooling system on the side of this inverter. So if you start seeing that you have a coolant leak and you see it's an external coolant leak, well, you're going to need to take the converter apart, scrape off all the RTV, put another coat of RTV back down, it'll be a solid fix. Now, why do they have coolant going in there in the first place? Well, remember that heat sink we were talking about, where all those other components bolted down to it? This is what the bottom of the inverter assembly looks like. There's all the cooling fins. Coolant will be circulating around through the bottom of this. So, and there's even a little bleed on the side of this to get the air out of the cooling system. So, we just went through what these components were and what their purpose in life was. So let's put our analytical thinking caps on here for a second. Let's talk about it. If I'm looking at data stream and I determine, hey, the 12-volt battery keeps dying in this car, right? What would I want to look at on data stream? I want to look at stuff having to do with the converter assembly, right? Because I'm diagnosing a charging system type of complaint. If I'm looking to see if the AC compressor is getting power when I turn it on my scan tool, well, I just saw where that originated from, how it came out of the inverter converter assembly. If I'm noticing that, hey, I have other types of issues, we're going to go over my go-to list of data stream PIDs of how we're going to use these to help us diagnose these electric vehicles. But before we get into that, I want to talk about the next component, right? So the next component that we have on the docket for tonight is a motor generator. So again, it's very much like the alternator. So here's the rotor assembly, and then here's the stator windings. And I got the 3 phases just like I had on an alternator. So we're getting a little ahead of ourselves. We're not going to talk a whole lot about that yet because we got to understand how this is designed to work. So make myself a little bit of room over here. It's common knowledge that this rotor assembly is in one shape or form attached to a drive wheel. Now, depending on how much voltage I give it, this thing can spin extremely fast. So that's a nice thing about electric vehicles, is you can use math to figure stuff out. So for instance, I don't have all of them committed to memory, but on a Chevy Bolt, the maximum speed that car will ever get is about 94.7 miles per hour. The RPM of the input shaft of the rotor assembly maxes out at just under 9,000 RPM. I can't spin a wheel at 9,000 RPM. I'm going to smoke the tire right off the rim. On a Tesla, the math is all different. That will spin at about 17,000 RPM. I can't spin the wheel at 17,000 RPM either. So this is a fairly simple concept. So this is a little device I got off of Amazon that I use in classes. I got, a couple dozen of these things that we use in live classes. I've already assembled them all, but it's easy to understand gear reduction because we've done timing chains and timing belts and stuff like that for years. So that's not really the big focus point here. But picture this orange handle as the wheel on the vehicle. Here's the motor assembly on the other side. The speed of that input shaft there is going to spin that little gear extremely fast. However, through the gear reduction, it's going to tame down how fast the drive wheel can actually spin. So at this point, I usually ask people, because that is a pretty simple concept that we can all grasp, but here's the positive and negative feeds. So here is my high voltage battery pack on an electric drive vehicle. Here's the driving motor, there's the tire. So I always ask people, what's it going to take to get this motor to start spinning? And everybody says, well, we need voltage. So I say, okay, and everybody's got their own, so they're going to be doing this themselves. It's not just going to be me. And it's a little bit hard to do on camera because you kind of need a third hand, but I'm going to just put the battery down on the table here momentarily, and I'm going to hook up my leads to the actual motor assembly. So now I have a connection, but that wheel's not spinning. So what am I missing? Well, I'm missing the magnetic field that's needed. So here I've got my magnetic field, and if I take these magnets and put them by the actual motor assembly and hook this back up to my battery pack, we're going to notice that that wheel now spins. And it's a pretty simple concept to understand that if I was to reverse the polarity, that motor is going to spin in the opposite direction of what it just was. So there I'm reversing the polarity, now it's spinning the other direction. So how does the manufacturers make the car go? Well, we just saw that. How do they make it go in reverse? Well, we just saw that as well. A very simplistic explanation. Now, what about this regenerative braking, right? Because you probably went to some training classes and they told you regenerative braking is anytime the rotational speed is greater than the magnetic force, right? Okay, what does that really mean? Well, I'm going to show you what that means. So I go ahead and I now take my motor leads. I don't have a high voltage battery supply going into it anymore, but I'm going to hook up this little LED light bulb, and we're going to show you regenerative braking in its most simplistic explanation here. So, on an electric drive vehicle, you step on the gas pedal, the high voltage is being sent to the motor generator, it's making the car go either forward or backwards. It's immaterial which way. As soon as I take that voltage away, this wheel, however, through inertia, is still spinning. So as long as that's still spinning, I will now create a generator, and I don't know if you can see the light bulb lighting up. I guess you can a little bit. Lots of lights in the studio, but I guess you can a little bit. So while we're slowing the car down from that inertia of that wheel that keeps spinning, the motor becomes a generator. We can use that to help charge the high voltage battery pack. So there's a very simplistic real world explanation of a motor generator and also regenerative braking. Now, it gets a little bit more complicated than that though, which is why we're going to graduate up. So, we can't send just a regular DC signal to the motor generator on a vehicle because it needs to see some sort of alternating current for this to work properly. So what I did is I went to the store, bought a brand new 12 volt brushless drill here, and I've got it hooked up to my scope. So I'm going to go ahead and activate this, and usually we start off with a digital voltometer and we just do a voltage test first, and then we do an actual frequency test with a DVOM. But because we have a limited amount of time, I want to give as much information as I can in the time that we have here tonight. So I'm just going to go straight to the scope. I never drilled one single hole with this drill assembly. I've got this thing hooked up. Took me a little bit of time to figure out which wires to hook to because I don't have a schematic for a DeWalt drill here, but I got on the 2 wires that I want. And I'm going to go ahead and turn my drill on, and then I'm going to freeze the pattern. Now, obviously it's a variable speed drill, so the faster I go, the more of those would be displayed on the screen. So if we look at the screen, we can clearly see that this is somehow creating what looks to be like a really weird AC signal, right? So how's it doing that? Because 0 is right where the ground line is on the left-hand side there, and we see that we got spikes going above and below ground. So I'm going to go ahead and I'm just going to make this pattern a little bit different, right? So I'm just going to use my fingers to expand this pattern a little bit. And as I make it bigger, what am I actually seeing? Well, if you've been around scopes for any length of time, you know that digital square waves are DC patterns, right? But again, that's actually what I have. That's not a sinusoidal type of AC type of waveform. That's actually what I have, but I have these DC patterns going above and below 0 volts. So that is a simulated AC signal being sent to the motor generator. Now, we call that pulse width modulation, right? So in essence, the frequency will change based off of the input, the most important input on an electric vehicle, which happens to be the gas pedal, right? So the further down I push that gas pedal, the more those IGBTs, as well as the actual motor generators and MOSFET relays, they have to change the frequency that they're sending to the motor generator stator windings, right? And we're creating an electromagnet at that point at the stator windings. Not necessarily the rotor. The rotor could be permanently magnetized. So we'll talk about rotors here in a little bit. But here's what we're seeing right here. So we're going to talk about some different data stream PIDs on how we can actually see this. We can do these live tests on an electric vehicle. If you work at a dealership, the dealership's probably going to tell you to test the motor generator windings with something called a milliohm meter. Now that's an expensive ohm meter, right? You might say, well, hey, my digital volt ohm meter reads milliohms. It does, but it doesn't read to the lowest quantity that we need it to. So what's the difference between a regular digital volt ohm meter and a milliohm meter? Well, in essence, it's the way the meter is calibrated, but primarily it's how the meter works. Here's my positive and negative leads. Notice that there's 2 red wires going to this lead and 2 black wires going to this lead. What's up with that, right? A regular digital volt ohm meter just has 1 red wire and 1 black wire going to, you know, the point or the alligator clip or whatever. So these are called Kelvin clips. And what's basically happening, just like it does with any digital volt ohm meter, is when we're measuring resistance, we're measuring for a voltage drop. So on a milliohm meter, we are sending a little bit less than an amp of current on one of the leads, and then we're measuring that voltage drop. That's how we're able to get those very small milliohm meter readings of, say, 20 milliohms or whatever the manufacturer says that is supposed to actually read. And they would tell us to test it by looking at each one of the 3 phases, jot down our readings, and then also test it to ground. So if I hold up this stator winding, I'm going to be testing the milliohm resistance between each one of these 3 phases. Then I'm also going to be testing to ground, which would be the actual armature style part of this assembly here. So in that case, I'm checking for any type of short. Now, the laws of electricity never change. So with that being said, we have to remember that, because on a regular 12-volt circuit, if I have a short, what happens to current? Current's going to go up. When current goes up, what happens to temperature? Temperature increases. That's how a fuse is actually designed to blow, right? Nothing changed as far as the laws of electricity goes when we're dealing with high voltage vehicles. So if I happen to think I had a short while I'm still in the driver's seat, just scanning my data stream, I would look at possibly a torque PID, because if one of those motor generator windings are shorted, it's going to affect the torque of the vehicle. Then I always want to back stuff up, right? So I would go ahead and look at, in this case, a temperature sensor by that motor generator stator windings, right? Because if it is shorted, if I'm on the right track, I should be taking little Legos and building them up, the little building blocks, to say, I'm definitely on the right track. I know when I get out of the car, I think I got a shorted motor winding, and I'm going to go right to that specific test. Now, at that time, I can either do a resistance test or an actual dynamic test, right? If you've taken any of my drivability classes over the year, you know that I very seldom do resistance testing. Now, if I worked at a dealership and for warranty purposes I had to document the resistance of that, I would, obviously. But if something's gonna fail, it's probably gonna fail dynamically as opposed to statically, right? So that's why I prefer doing testing with not an ohm meter, but something like a scope, right? And again, the laws of electricity don't change. So it would, if I had a shorted winding, it would show up dynamically on my scope pattern as well. So this drill obviously does not have any shorted windings in it. But if I had a shorted winding, it would show up dynamically on my scope pattern as well. Now, one thing I just want to throw out there is if you do happen to have a scope and you're going to be doing these tests, it would be a live test, so you'd have to have your protective devices on. But your scope is going to need, since we're dealing with high voltage, you're going to need something called a differential probe, right? We're dealing with low voltage on that drill, which is why I didn't have to have this hooked up. So lots of different manufacturers sell these, right? And you can get one for, they're pretty much universal. The only thing that makes it different is what type of scope connector you have. So all my scopes use BNC style, so that's the ones that I bought there. But this is going to be needed. We need to use a differential probe for two reasons. Number one, it's kind of an attenuator, and you scope guys know what that is. But it will also, we need this because of the isolated ground that is used in high voltage circuits. Without it, you run the risk of damaging your scope, and you don't want to damage your scope. Now, for the guys that are non-scope people that say, well, I'm not going to buy a scope because I don't like scopes, but I want to test it dynamically. An alternative you have is something called a three-phase tester, right? So these little three-phase testers can be bought. Obviously, you got 3 wires, color-coded. You can't possibly hook them up wrong, right? So color-code them. You hook them up to the 3 different terminals of that stator winding, and then you cause the stator to work. On the screen of this here, it's going to use little LEDs that are going to tell you if there's a shorted solenoid, or if there's 2 shorted windings, I should say, or if there's 2 shorted windings or whatever. It'll even tell you the direction in which that is causing the rotor to spin, right? So this is what I call the poor man's scope. If you want to think about it kind of like a logic probe, how when scopes first came out, logic probes were around. If you couldn't afford the money for a scope, you bought a logic probe, and that was the next best thing you could get. Well, this is kind of the same principle when we're dealing with the high voltage. So this is called a 3-phase tester. Not real expensive. All right, so one last thing I kind of wanted to talk about real quick. Here's another little training prop that I assembled for our live classes. And I always pass out worksheets and stuff for the guys to do at the end of the classes, and we use the training props first, and then there's worksheets dedicated towards the cars that we have in the shop that day as well. So here's a motor generator. I've got the magnetic field, right? The difference is here, this is a pulse width modulation box. I've got 2 test jacks. I could hook the scope up to there, or a voltometer, whatever. But I have a forward and reverse switch, and I have a motor speed switch. So the motor speed switch is the equivalent on a car to the gas pedal, right? Obviously, the more I turn that switch, the faster that's going to spin. The further I push down the gas pedal, the faster the car is going to go. And then forward and reverse I thought was cool because that simulated, reversing the polarity. But I've learned from experience that the future boxes, because I got a bunch of these built for training classes, but the future boxes, I'm going to do away with that switch because we're mechanics and we like to get that thing spinning as fast as possible and then switch directions, right? And that's something that so far hasn't caused a problem, but, in the future, it can't be happy when it's happening, basically. So I'm going to grab my little power strip from behind the curtains here to plug this component in. I'm going to turn the power on here, and I'm going to go ahead and simulate what we just talked about. So as I increase the speed, so step on the gas pedal, it starts spinning faster, right? As I take my foot off the gas pedal, obviously eventually we come to a complete stop. Now the only difference between this, and this is a great teaching aid to learn pulse width modulation, the only difference is this does not simulate regenerative braking like a car does. But I think with that first little training prop really got that point across to everyone. So with that being said, let me just get this out of the way. I don't think we need to capture a scope pattern again because we have a limited amount of time together here tonight. So I'm just going to move this to the side. I want to talk about the rotor assembly. So the rotor assembly has a lot of little intricacies by itself. So here's a rotor assembly that is permanently magnetized. So there's a pocket screwdriver. I got it upside down. We are on planet Earth, so there's gravity that should be falling if there wasn't magnets there. All right, so with that being said, do all rotor assemblies have permanent magnets in them? The answer to that question is no. So I'm going to go back to the slide presentation real quick because I've got pictures of these cut up, and I'm going to fast forward to the section that talks about them. So there is the rotor assembly that I just held up that's taken apart. There you can see how the magnets are actually in place. And in a live training class, I actually have actual magnets that we pass around, and we talk about opposites attract and all that other stuff, and we talk about the air gaps between them. So, first of all, what's the advantage to having a permanently magnetized rotor? The advantage is I will have immediate torque. I'm not relying on an electromagnet that's going to be created once I send power to the stator windings to then get induced into the rotor. The disadvantage to a permanently magnetic rotor is that takes more power. More power gives you less range. So for all the ICE guys in here, if I went from point A to point B with my air conditioner running, I'm going to use more gas than if I did not have that extra load placed on the engine. Well, this is actually an extra load placed on the high voltage battery pack. Most car manufacturers use a permanent magnet. Tesla, however, there was a time that they did not, and they used what was called an induction motor. So let me just fast forward to well, I guess I don't have a picture of an induction motor. I apologize for that. But they used what was called a squirrel cage. There was no permanent magnets inside there. And then we would magnetize the rotor shaft through electromagnetism when we powered up the stator windings. It was great for range. There wasn't that extra load, but it suffered as far as torque goes. So Tesla, who never rests, decide we want the best of both worlds. And the best of both worlds is this. I want to have still great range, but I also want to have great low end torque. So they came out with the motor assembly that's on your screen now, which is the SYNR/motor assembly. And what that did was it uses permanent magnets, but if I change the spacing of those permanent magnets, you've played with these before, refrigerator magnets, probably when you were 4 years old. 3 years old, you were probably just eating them. But after that, you were probably playing with them, right? So you know that opposites will attract. If I turn them the other way, it wants to repel and everything along those lines. But I also know that I could take two magnets, and depending their strength, there comes a point as I bring those two magnets together that I can feel that magnetic field. And it wants to suck them together, right? Well, if I change that air gap, that magnetic field gets weaker. Because if I get them real close to one another, us mechanics have pretty strong fingers to begin with, but it's impossible in most cases, if they're decent sized magnets, to hold them apart, right? Because that magnetic field gets too strong. So when the rotor assembly is permanently magnetic, they have a fixed air gap. So that magnetic field is rated at whatever that turns out to be based off that air gap. What Tesla did here with their later model vehicles is they can actually change that air gap. You can kind of see that plate over the top of it. That's where the magnets would go in. And at different types of speeds, I can actually change that air gap. We're not talking changing it by 5 inches or anything, but just that little bit of change of those air gaps, of those magnets, allows them to achieve the low end torque, plus it doesn't hurt the actual range of the vehicle. So Tesla, my hat's off to you on that. You did a great job with that. All right, so we've covered quite a bit here, and I know we only have so much time together here tonight. So what I want to do is I'm going to fast forward here to this particular slide, and then we're going to go over a couple other slides together while we're in this presentation. Then we're going to hook up to this car behind me. So there is a rear motor assembly off of Tesla, right? So you can see that's pretty big in size. The whole thing's not a motor. Half of it's an inverter, right? This is the rear motor because there's also a front motor assembly. So you can see that obviously that's why Tesla at one time had the fastest production car car, because we always used to say as car guys, there's no replacement for cubic inch displacement. Well, electric vehicles have changed that. That's no longer a true statement. In next month's webinar, we're going to concentrate on the repair shop and the repair technician when it comes to working and servicing electric drive vehicles. So we've lost a lot of service potential, right? We can't do timing belts anymore. There are no timing belts, right? An alternator is not going to go bad. They don't use an alternator. So we lost a lot of service potentials, but the industry gave us new service potentials. So we're going to spend part of that next month's class on that kind of stuff. What are those new service potentials? How do we perform them? Stuff along those lines. We also are going to talk about what we need as a shop owner or as a technician to get ourselves prepared for the influx of all the electric vehicles coming into your service base. So it's not a very expensive investment. You know, definitely less than $10,000 in most cases will get you everything you need. Now, some of the stuff you may already have. So one of the things you need is a scan tool, right? Well, that's the majority of the $10,000 right there. You probably already have a scan tool, I'm guessing, right? So you could take that off the list. You may have some of these components already. But looking at the actual slide, when we're talking about an internal combustion engine, here's a huge advantage for electric vehicles. One of them is we don't have anywhere near the amount of moving parts we had in an ICE driveline. So I never counted them all, but it's definitely in the hundreds, right? I've got connecting rods, I got pistons, I got the actual bearings, I got a crankshaft, I got a camshaft, I got all these moving parts. And moving parts mean they're going to wear over time and they're going to eventually fail. On an electric vehicle, we will have about 21 moving parts. And on Teslas, we have even less than that. So we need to be aware of what those moving parts are, how they're supposed to work, everything along those lines. But we need to be aware of the fact that we can't even do oil changes anymore, right? Because we don't have oil. So we need to be aware of how we're going to service these electric drive vehicles, both safely, profitably, and efficiently. So I wanted to pull our attention to that slide there for a second. And then I want to talk about data stream. And then we're going to hook up to this car with our scan tool, and we're going to actually show this data stream live. So number one, I'm not just saying this because I happen to have an Autel shirt on. Autel right now, as opposed to, say, 3 months ago, has a feature that no other scan tool company has. So we all know in this industry that's short-lived. Eventually everybody's going to have it, but we're kind of proud of the fact that we have it right now. First out of the gate with it. So we know that on a traditional car, when I hook up and look at data stream, I'm basically taking a scan tool and I'm plugging into the OBD2 connector underneath the dash. So let's think about that. What am I looking at? I'm looking at the data bus lines of communication amongst all the modules, right? The only thing I can see is information that's shared from one module to another along that data bus network. So, and that's quite a bit, don't get me wrong. It's a wealth of information. What Autel has done recently is it has given us the ability with the inclusion of an EV diagnostic box to hook directly to the high voltage battery management system. Now, we talked about that last month's webinar. We showed it to you. We showed you screenshots of stuff being in use. We showed you, how to use it, the importance of being able to do it. If you happen to miss that webinar, eventually you'll probably be able to find the recording on YouTube. Autel's policy is if you registered for the webinar, you'll get a link immediately. If you didn't register for the webinar, it usually ends up on YouTube about 60 days later, right? That's the advantage to actually seeing it, or at least registering for the webinar, right? You get to see it immediately. So with that being said, we know that there's a difference between them. A good friend of mine, another coworker here at Autel, one of my 150,000 bosses at Autel actually, his name is Mike Flink. In fact, you might be thinking that this is Mike Flink talking to you right now because I'm using his account in GoToWebinar to set this up. Last month, he's like, hey, everybody kept giving me insights thinking I taught the class, right? Because I'm using his account. But with all that being said, he had a great terminology. When we talked last month about state of health and state of charge and being able to recalibrate that, he's like, the industry just gave us our new tune-up. So the car manufacturers say to do that every 3 to 6 months. That's a recommendation. I can now tell the customer, if you let me do this on a regular basis, I am going to extend the life of your high voltage battery pack. I'm also going to be able to get you back some of those missing miles of range. So it's a very common complaint. When the car was new and I'd charge it up, I had 300 miles of range. But as of late, it's dropped down to 282 miles. Does that mean my battery is going bad? Well, maybe, don't know. But let's do this recalibration because pretty good chance that that's going to get you those missing range back up. So the guys that watched last month's webinar, you guys understood. We went over in great detail how that happens and why it happens. It happens with any battery, it doesn't matter. For the guys that did not see that, I'm not going to go in as great a detail, but basically over time, the internal impedance of the battery cells will change. The impedance will get higher. That affects the state of health and state of charge. So it never fully charges that battery pack again because it has nothing to base it off of. It's just like that electric drill, wherever it ended up over here. You know from experience that you hear, depending on the type of battery, sometimes it's okay to leave it in the charger forever. Other times they tell you, put it in the charger, but don't leave it in there. You're going to shorten the battery life, right? That's what we're talking about here when we're talking about state of health. So we, as consumers, have range anxiety, which means we don't want to be stuck on the side of the road with a dead battery on an electric vehicle. So what most people do is they never let that battery go from a state of charge that's near 100% down below 20%. It gets to be like 30%. Their number one thought on everyone's mind is, well, I got to find a charger. I got to charge this thing up, right? Well, without that big deep cycling of that battery, we run the risk of changing the state of health and shortening that battery life. So at a dealership, a lot of times what they'll do, sometimes they have special service modes where you got to put your foot on the brake and hit the start button in a certain sequence and stuff. But basically they're making that high voltage battery drain, right? And then once that battery is drained below 20%, they tell you to use a level 2 charger, which we talked about last month as well, a level 2 charger, and not only charge it up to 100%, but monitor that voltage until it's not taking any more current from a level 2 charger. Can't use a level 3. It would take 40 hours or so to use a level 1. So it has to be a level 2, right? So then once it stops accepting any more charge, then that is how they accommodate that balancing. Well, that could take, 45 minutes, an hour, hour and a half, depends on how much voltage was in the battery when the car was dropped off. Autel has that bidirectionally in it. It takes about 10 minutes to do. We are bidirectionally draining the high voltage down. We're turning a bunch of different loads on, basically, which is what's causing that high voltage battery pack to drain. So that is a good selling feature for your customer because customers do not want that $20,000 bill that they keep hearing about when their high voltage battery goes bad. It's a way to make sure that they get the optimum life expectancy out of that high voltage battery. All right, so let's talk about my helpful go-to PIDs. And if you've taken a drivability class from me, you knew that I had 6 PIDs. Those 6 PIDs would tell me what area is causing the problem, right? I would then formulate, when I got out of the driver's seat, an attack plan. So if I knew it was a fuel system related thing, I know how to do all the different fuel system testing. I want those test results, but when I open the hood, it may be too hard to do test A. I still need the test results though, so I had to think outside of the box on another way to get those same test results. Well, this is what I'm applying that same knowledge to electric vehicles. They're not 6 PIDs, and they're not obviously not the same 6 PIDs, right? There's probably about a dozen or so PIDs. But I'm just going to share with you what those PIDs are, and I'm going to tell you what I use them for. Some of them I'm using to help verify what I'm thinking is wrong by looking at a different PID, right? So the first one is anything temperature related. Throughout an electric vehicle, I have thermistors inside the high voltage battery pack. I have thermistors inside the inverter assembly, converter assembly, as well as the motor generators, right? So we'll use a motor generator as an example. If I thought I had a shorted winding, again, the laws of electricity don't change. Well, if it's shorted, increase of current, which also increases temperature. So I can use that to help back up my initial suspicion, right? I didn't find the shorted winding off this temperature PID. I'm finding it off a different PID, but I'm backing up my suspicion with that. Now, I'm still in the driver's seat just looking at a scan tool. I use the same philosophy, and we use motor generator as an example, but the same philosophy is going to hold true whether or not it's a cell problem inside the high voltage battery pack. I use those PIDs to actually test the cooling of the high voltage battery pack, the heating of the high voltage battery pack, the cooling of the inverters and everything. You guys know I'm not sharing any wealth of knowledge here about temperature PIDs. This is what I'm using it for, right? Now, if I go to my next helpful PID, this is going to be any of my torque related PIDs. So that is what I'm first looking at if I'm thinking in my head I have a shorted motor generator winding. Or possibly I don't have a shorted, so let's say the complaint is I step on the gas pedal and this thing just doesn't want to go. It's slowly creeping up, right? It's not responsive like it's supposed to be. So knowing what we talked about tonight, you're going to say, I remember we had capacitors that got charged, and I remember we have the high voltage, and I remember there was this boost thing, and I remember that when we took a stationary object and wanted it to move, we gave it extra voltage to get that going. So I could find a shorted stator winding with the torque related PID, but it could be anything that we just talked about there too that causes that type of complaint of I step on the gas pedal and this car is just barely creeping through the intersection, right? So I look at that PID first, and then if I want to say, I wonder if it's a shorted winding, then I would go look at the temperature PID to use as backup. I'm not done yet. I'm going to look at other PIDs too, but by the time I leave that driver's seat, I know, hey, it's a shorted winding that I'm going to go to for an actual hands-on test, or it's something inside the inverter assembly that I got to go to for some pinpoint testing, right? So let's go to another PID. I have MG phase related PIDs, so motor generator phase related PIDs. There's something called a resolver. We know that 3 phases, 360 degrees in a circle, so if they're equally spaced apart, they should be 120 degrees apart apiece. If I use a lab scope, this is another benefit to testing something dynamically. I could have 3 channels hooked up. Now remember, I'm going to have 3 differential probes, not a big deal. I can look at all 3 of those phases simultaneously, all under load, right? So I would be able to determine if I have a shorted motor generator winding if I did that live hands-on test. Another clue that I have is by looking at those resolver PIDs, because if I do have a shorted winding, it's going to affect that 120 degree reading on my scan tool. Now, I'm going to also look at my inverter or high voltage battery, or possibly, so I have 3 cooling systems on most electric vehicles, right? We'll start with that. I have a cooling system that's being used just to keep that guy, the driver inside the vehicle, that person, got to be politically correct, that person inside the vehicle warm in the wintertime, right? So that is one cooling system. And then most full electric vehicles will have a separate cooling system just for the high voltage battery pack. And then they have a third cooling system to keep all the rest of the electronics cool, right? Because when we're flowing electricity, byproduct of that is heat. So the battery one has to be kind of unique though, because in order for a battery to work properly, we need it to be in its optimal temperature range. So that range, remember from last month, is between 68 degrees Fahrenheit up to about 97 degrees Fahrenheit. Which basically means that if I park this car outside on a winter day or a cold day, I will, even though it's powered off, I will drain the high voltage battery. Because in that scenario, at times, if battery starts to get too cold, it's going to want to turn the cooling system on to heat up that battery. Now, if it's a hot summer day, it's the exact opposite. It's going to want to cool off that battery pack, right? Which is why we said last month that every shop needs a level 2 charger, because you have to be able to diagnose charging complaints when they come in, but you also need to be able to take a car that has discharged while it's in your shop and charge it back up for the customer. You can't give them a car back with 3 miles of range and say, oh, here's your bill. By the way, you need to find a charger on your way home. Hopefully it's within 3 miles because that's all the range you have left in your car, right? Nobody's going to want that, right? So those 2 reasons is why you need some type of charger. True, the car comes with the charger, but it's probably a level 1 charger, and it's going to take way too long to get some kind of substantial charge, and our profit structure does not dictate us giving up a bay for 10, 20, 30, 40 hours to charge up a battery pack. We're going to be going out of business if we did that. So if I have multiple cooling systems, I will have multiple types of radiators. So I'm using the inverter radiator as an example here. But if for some reason the inverter radiator, all the temperature related readings coming from that high voltage system is telling me everything's running hot, I'm going to go ahead and say, okay, so the inverter, the converter, and the motor generator are all running hot because the battery on an electric car has its own cooling system most likely. So what could cause that? I could have a component, right? But that's very, very unlikely, because if I have a component that's shorted, it's probably only going to increase the temperature in that one area of the car. No matter what I looked at, all 3 of those components are running hot. So I could have a coolant leak, right? So I could not have any coolant in there. I could also have the electric coolant pump may not be cycling. But I'm going to differentiate what I'm going to do by looking at these temperatures. So again, we got 3 different cooling systems. I'm only going to use inverter as an example, but I also have a battery radiator, right? I also will have another radiator for that person inside the car, right? With coolant pumps and everything else. Every single component has a way to measure the voltage and amperage. So your voltage and amperage PIDs become huge as well. So, for instance, here's my IGBT. Remember, those bus bars attached to the IGBT, and then the other side of the bus bars had the little orange cable that went down to the motor generators. So, if I have a shorted winding, right, I can probably even tell you which winding it is that I'm going to test first by looking at my scan data, because look what's happening here. We have an inductive little clamp around these terminals. So I'm getting an amperage reading from the 3 different phases here. So I know I have an amperage thing that's telling me it's too high. My temperature is telling me that it's too warm. My torque PIDs are telling me that there's a problem with this. So I start gathering all this information together and I say, I definitely feel pretty strongly that I have a shorted motor generator winding. In fact, I can probably even tell you which one I'm going to go to and test first, right? So that's how I'm talking about using these PIDs together to form this attack plan. I have amperage PIDs and voltage PIDs in the high voltage battery pack, which we talked about last month. We have them in the converter assembly. We have them all throughout an electric vehicle. I've seen one of these go bad in real life, but I use this PID to protect my life more so than to diagnose cars, right? So remember, those capacitors get charged. They have to get discharged when the car's powered down through some kind of resistor. I have a resistor PID. If that resistor is burned open, I know that I'm never taking my gloves off when I'm working on this vehicle, right? So I'm going to want to prove it with the live dead live test afterwards, but I kind of have an input that is always going to have stored energy inside the capacitors. And you're never going to see me take my gloves off until that stored energy has dissipated, right? Now, with that being said, I also have all my AC related PIDs. So if this electric vehicle comes in and they're complaining about air conditioning, right? Well, it's not like the old days where, does it have Freon in it? That's still pretty much the same. I can test that. But let's say it did, we would take like a test light or something and back probe the connector and say, well, is it getting power when I tell it to turn on, and that kind of stuff, right? Use a scan tool bidirectionally to tell it to turn on, check for power. Well, I can still do all those same things with my scan tool. I can also go ahead and take my dedicated high voltage voltmeter and I can unplug the connector while I'm gloved up, because it is high voltage, and I can measure to see if voltage is getting to the compressor. Or I can look at my scan tool PIDs for the air conditioning, right? Did it get the signal? So did the signal go from the control head in the middle of the dash along the data bus lines of communication? Did it go through the proper chains here? And is it getting the proper signal at the compressor, right? So I use that for anything air conditioning related. My contactor PIDs, again, that we covered last month, but I can tell you if those contactors are opening and closing, and if we command them open, did they actually open? Because just like a relay, those physical points could get arced shut. Now, in theory, that is a very dangerous scenario, because if they're arced shut, that high voltage is never staying inside the high voltage battery pack. It's powering everything up. So I never want to take my gloves off, right? Until I prove that that high voltage thread is gone. Well, I have a good insight as to the operation of those contactors with my contactor PIDs. My battery state of charge and state of health, we covered that in great detail last month. My lowest and highest battery block PIDs, right? Or battery cell PIDs or battery module PIDs or whatever that manufacturer happens to want to call it. This is important because this is when we set the out of balance related codes on an electric drive vehicle. Every manufacturer has, just like the Mode 6 stuff, they have a testing strategy, and if it exceeds that window, that's when a trouble code actually stores, right? So sometimes it's very small. They can't be more than 250 millivolts apart from one another. Other times it's larger. It could be, maybe a volt and a half apart from one another. But this is important because I can actually quickly look at that and get a pretty good understanding of how properly balanced that battery pack is. Now, the next thing is all of the individual battery block or module or whatever they want to call it, PIDs, right? So I will get an individual voltage from every one of those individual cells. So now I can see, hey, look at that. I've got, if there's 1,000 individual lithium cells, I've got maybe 25 that are reading way less than the rest of them, right? Well, there's a prime example of when I know for a fact that doing that calibration is going to help, right? So I can almost guarantee my customer that they're going to regain that lost mileage. The battery is starting to fail, right? But I'm going to do that tune-up. And that tune-up is going to bring this battery back to life and help extend the life of that battery. All right, so those were my go-to PIDs that I like to use whenever I'm looking at an EV vehicle. The car behind me has a check engine light on because this is actually a plug-in hybrid. It has a check engine light on for EV-related, for EGR-related diagnostic trouble code. Don't care about it. This is the car I borrow from my friend whenever we do something in the studio here. Depending on the extent of what we're doing, sometimes I borrow another friend's Tesla and another friend's Prius, right? But for what we did here tonight, this car will work just fine. We don't care about going into the standard system here of the internal combustion engine stuff. So I'm just going to plug my little box into the OBD2 connector. We're not going to go to the battery management system like we did last month. I'm going to power up the car. The car gets recognized right away. That's another new feature that one of the latest updates that Autel did. So it says, hey, this is the car, this is what you want, right? I'm going to tell it not to do that, right? The reason being is because I'm going to show you what the differences are. So on the screen of the scan tool, you kind of see a different look than what you're accustomed to from Autel products. So normally we would just have that red box that said Diagnostics. Well, that would take me to anything that I want to do through that OBD2 connector on a non-hybrid or EV related car. With this new update, if it actually is a hybrid, a plug-in hybrid or an electric vehicle, I'm going to select the green box that says EV, right? The other green box that says EV, that underneath it says battery pack test, that's how I go into the battery management system test. That's if I was plugging directly in to the high voltage battery. But I'm going to go ahead and say new energy. Again, it comes up, tells me, hey, this is a car. So I'm okay with that. I'm going to say okay. It's a Chevrolet. Got to do the standalone. I'm going to turn that off here one of these days. There's the VIN. I'm good with the VIN. I'm going to say okay. It's going to come through. It would ask me if it needs further assistance. So like, does it have parking aid sensors? Might be a common thing it asks you or something. This one was able to talk to it because we've used this in different classes so many times. I'm just going to say okay, we're good. We're going to let it connect to the computer. It's connected to the computer. Now, I can do an auto scan, and auto scan is going to take me into the topology screens, and that's great for diagnosing data bus communication faults and seeing what all modules, are talking, what all modules are available, all that kind of stuff. But I want to go into the high voltage system diagnosis. Here it gives me a list of different types of modules here. I can do a fault scan on these modules by themselves, right? I'm going to go ahead and exit out of here, and I'm going to go into a specific module, and I'm going to go into, just for an example, the drive motor control module number 1. I'm going to select live data. I'm going to let it talk to the car, and we're going to pull up some PIDs. So, my words of advice is this. Those PIDs that I talked about as the go-to PIDs, and I think we got the point across how to use them effectively, they're going to be found in different modules in different parts of the scan tool. So you will have to go to different areas, right? So here, since we kind of use as an example shorted motor generator windings, I went there first, right? We're not going to go through all the PIDs because I think you guys got a good grasp on what I'm using these PIDs for. But here I can see typical data stream for a motor generator, right? And this is drive motor 1. So I've got my ignition signal, which is 12 volts, right? In the converter, forgot to mention this, if I wanted to turn this car into a cop car, right? Normally I'd have to put lights on, sirens, all that stuff. Well, on an old-fashioned car with the charging system, that was pretty easily done. We can change the alternator, we can change the voltage regulator, we can accommodate those extra loads. How do we do that with an electric car? Well, we can't, right? Because the DC to DC converter is going to put out a specific charging system voltage. So it's usually just under 15 volts. It's never going to change. So in order to accept those extra loads, I actually have to change the size of the 12 volt battery in the car. What that basically does is when I got all those loads on and I'm actually not creating that charging system voltage, I'm discharging the battery, but that's okay because as soon as I shut those loads off, I'm going to be able to charge that battery back up as opposed to the real small AGM battery that came with the car. I have to replace it with an AGM style battery, but I'm using one with much bigger battery reserves. So I see this. I got my hybrid EV high voltage circuit here, saying it's got about 395 volts roughly. I got my drive motor 1 current. Right now the car's not going anywhere, right? So I'm creating a negative amperage there. So if I started to accelerate it and I had a shorted motor winding, that's going to affect the overall current, right? Because again, if it's a short, it affects current. If it's open, I guess the opposite would happen too. My drive motor 1 speed, my drive motor 1 torque, so this is where some of these PIDs are that we were talking about. Notice there's my drive motor 1 temperature sensor inputs, and I have 3 temperature sensor inputs there, right? So I'm not just basing it off of one, because if I use this and I said, I think I got a shorted motor generator winding, great, but one of them is saying it's way less or way higher than the other two, knowing how in close proximity those sensors are to one another, I'm not thinking a shorted motor generator winding at that point. I'm thinking I have a bad temperature sensor. But if all of them were reading hotter, well then that scenario of a short, I'd want to go with. Drive motor 1 inverter status, active. Drive motor 1 position sensor, hasn't ran yet. Drive motor 1 inverter supply voltage circuit. So here we know, we established earlier on that the inverter supplies the voltage to the drive motor. So we'll use this as an example. Customer's complaint is I step on the gas pedal and maybe the thing just barely creeps. We know that there's a lot of components involved here. One of the first things I want to know is where is the lack of voltage coming from, right? So I know it originated at the inverter. I see that I got 395 volts there. Up a little bit, we already pointed out what the actual drive motor voltages were, right? So this is how I'm using this to kind of do like my own little flow chart to see, you know, where the problem could lie here. So again, I have multiple different PIDs available to me, and because this is a short time frame of a class, I could literally go on my live classes anywhere from 2 solid days all the way up to a solid week for hands-on training. Depends on how much hands-on you want, right? So that's the difference between them. But we only had an hour and a half here together. But I want to go ahead and take a look at some of the questions that people might have. And if I look at the actual questions here to see if anybody had any. Are there any manufacturer EVs not supported by Autel? So here, that's a very good question, and a lot of people ask this a lot. And I know I work for Autel, and you are probably going to think that I'm just going to say good things about Autel, but I'll be totally honest with you. Autel is
the only scan tool out there right now that does the things that we talked about last month, where I can hook directly to the battery management system. Now, all other scan tools, including this Autel one too, has the ability to hook up to the OBD2 connector and see any information that the manufacturers share along the data bus lines of communication. So in that aspect, it's very similar to any other brand of scan tool out there. But where it really shines is where it goes into the battery management system. By being able to go into the battery management system and opening up the ability to recalibrate the state of charge and state of health, and being able to see all the temperature sensors instead of just an average temperature sensor inside that battery pack. The reason why all this is so important, it's not only just for diagnostics, but the high voltage battery pack is the most expensive component on an electric vehicle. And we want to do anything we can, and our consumers want us to do anything we can to help prolong the life of that battery pack. They don't want a $20,000 bill saying, hey, the battery's out of warranty after 8 years and you need a new high voltage battery pack. They're going to be thinking, hey, the car might not even be worth that, right? So what do I do with it? If I go to try to trade it in, they're not going to give me anything because they know the high voltage battery is bad. So there's so many reasons behind that. With the ability to recalibrate the state of charge and state of health by itself, and I'll take this from one of my bosses. I have about 100 bosses at Autel, but from one of my bosses, Mike Flink, he came up with a great saying when we were at the Apex show. The automotive industry basically gave us our tune-up back. So by us being able to recalibrate that state of charge and state of health every 3 to 6 months based on the manufacturer's recommendations, what's the same as what we had in the old days when we brought the car in for changing points and condenser on the car. We haven't had a legitimate tune-up like that in decades. Well, we now have a way that we can come in and we can not only use it to help generate profits for our shop and generate work for our shop, but our consumers are going to thank us because we are, in essence, prolonging the life of that high voltage battery, which is huge, because again, nobody wants that $20,000 bill. And even if it's not a Tesla or one of those $20,000 batteries, they don't want a $3,000 bill, right? So let's say it's an old-fashioned Toyota Prius that's not even a plug-in hybrid. Well, those battery packs are like $3,000, $4,000. They don't want that kind of bill. So, and then anything higher, they obviously don't want either. So that is something that is very important. Autel will support all the different electric drive types of vehicles out there. They'll support it through the OBD2 connector, just like other scan tool manufacturers do. Now, hooking up to the battery management system, there's probably about 18 different car manufacturers globally that the Autel scan tool supports right now, hooking up directly to the battery management system. Since I live in the United States, I'm mostly concerned about the cars that I see coming into my shop. Autel doesn't just do the United States cars. They do the ones in Europe and overseas just as well as they do the ones here in the States. The one complaint that I have, I wouldn't say it's a complaint. The one suggestion I gave to headquarters is when you get the EV Diagnostic kit, it comes with probably about 30 to 50 different made up cables going into the battery management system. And if I pull out, the Tesla cable, or if I pull out, a Mercedes cable or a Porsche cable, that is a pre-molded cable that all I have to do is unplug the factory cable and then plug this other one right in. If I pull out a Chevy or a Ford, I have to use a universal pinout cable. Now, from what I'm hearing, it's just something that will eventually be released in future updates. But I said to them, I'm like, as a technician, none of us want to do that. You do a great job. You show us the wiring diagram on the screen. there's no confusion exactly where to put those pinouts, but it's so much faster and easier to be able to just go ahead and unplug one connector and the other connector just plugs right into it. So that's something that they're working on, making extra cables in the future. Autel also had Tesla cables for, I want to say, and don't quote me on this, but I want to say probably at least 2 to 3 years. So with the Tesla optional cables, they don't come with any one of our scan tools, but with the Tesla optional cables that you buy, I can plug in and get live data on a lot of Teslas. And I emphasis on live because the supporting scan tool that Tesla went ahead and released here, that gave us screenshots. So I'd much rather have live data. Now it's still a Tesla, so that still is kind of a drag in some cases because they obviously don't use an OBD2 connector, and they use 3 different versions of connectors, different places on the vehicle. So you have to have a little bit of Tesla experience, but Autel was one of the first that actually did that as well. So what I like about Autel is, as far as their diagnostic scan tools go, they work on a lot of cars really well. You know, it's not an OEM scan tool, but you know, sometimes I'll get a service call, some shop will call me up and they'll say, hey, can you code this module, right, on some weird car? And I'll say, I don't know, but I'll give it a shot, right? Because so far, every time I've asked my Autel to do something that I'm not sure about, it's been able to do it. Now, it's still a scan tool and it's not, you know, perfect for everything. So are there any manufacturers EVs not supported by Autel? I haven't come across one yet. I'm sure there might be something somewhere, but I personally haven't come across one yet. We have, any EVs require an internet connection to connect to a vehicle? I guess it would depend on what you're trying to do to that vehicle. So obviously programming or something like that, you'd have to have an internet connection to. I don't know of any EVs that I've personally worked on yet that required an actual internet connection to look at scan data. And when you're looking at the battery management system, you definitely don't need internet services because the battery doesn't even have to be in the car. It could be sitting on a bench somewhere and you can get the data that you need out of the BMS on the vehicle. All right, so I'm looking to see if there's any other types of questions. Battery charging and that analytics available on Autel EV. For instance, being able to pull data for last 10 charges. So yes and no. So, and show battery state of charge or state of health. Yes, that state of charge or state of health is available on the Autel, 100%. For the last 10 charges, so Autel uses reports, right? So what that would be more on the car manufacturer side if they can actually store it in some module on the vehicle. So whether it's the onboard charger module or whatever the case happens to be, as long as it has that ability to, then the Autel can do it and you'd be able to print out a report and actually see that. Otherwise, you'd probably have to go into the separate 10 charges in that example and pull them up one at a time. But if you were able to print out the report, you'd be able to see it all at once. Next month's webinar, or it may end up being at the beginning part of January, just depending on the schedule, because obviously next month is Christmas and there's a lot of holidays coming up here. But the next webinar relating to high voltage is going to be on what an auto repair shop needs to prepare for the influx of electric vehicles and what an auto repair shop needs to know to accommodate for the lack of other types of work. So obviously we're not going to have timing chain jobs anymore. We're not going to have Brakes are going to last, 100,000+ miles because of regenerative braking. So what does an electric vehicle offer that we need to know as auto shop repair owners to be able to, still service our customers' needs and still, recuperate, some lost revenue that we have from the change that's happening here. So I'm going to end today's session here, and I will look forward to seeing all you guys next month. Remember to email me if you have any questions that come up, and also be on the lookout for a link of the hands-on section of tonight's webinar. Thank you for attending, everyone.